जय हिंद स्टूडेंट्स, आप लोग कैसे हैं? I hope you all are staying fit and fine. So students, today we are going to discuss the effects of current. There are actually various effects of current. Like one is heating effects of current, second is chemical effects of current, third is magnetic effects of current. So today in this particular session we will discuss the heating effects of current. And before that, I must state about electric energy. Now, how to define electric energy? Now we are aware that electrons, in the absence of any external source inside a conductor, tend to move randomly about here and there. They do not constitute any electric current. But what happens is, when the two ends of a conductor is maintained at a constant potential difference, then electrons tend to drift in a particular direction. And that is when electric current flows through the conductor, isn't it? So what I mean to say is that in order that a current flows through an electric circuit, a source has to spend some energy in maintaining potential difference across the ends of the conductor. So that energy of the source of EMF in maintaining a constant potential difference so as to enable the current to flow through the circuit is known as electrical energy, right? And students, James Joule found that when this electric current is made to pass through any conductor for a given time, then the conductor tends to get heated up. So this effect, which was first studied by James Joule, is known as Joule's heating effects of current. So we'll start with heating effects of current. First we'll discuss it mathematically and then we'll discuss it qualitatively, right? So what we'll do is, we'll start with heating effects of current. And as I've stated, this heating effects of current was first studied by James Joule. Suppose this is a conductor, any conductor, offering resistance R. Now suppose the ends of this conductor, A and B, are maintained at potential VA and VB. Let us consider VA to be greater than VB. Then you are aware the conventional current, it will always flow from higher potential to lower potential. So the potential difference would be VA minus VB. Let it be represented by V. So under the influence of this potential difference V, the current through the conductor flows from one end, that is A, to the other end of the conductor, that is B. And we have assumed the conductor to be offering resistance R. So what James Joule found was, amount of heat is produced whenever current is made to pass through a conductor. And this amount of heat produced across the length of the conductor is found to be directly proportional to the square of the current flowing through it. So H is directly proportional to I square. So if the current through the conductor is made twice, the amount of heat produced will become 4 times. If the current through the conductor is made 3 times, other factors remaining same, then the amount of heat produced will get 9 times. So what I mean to say is that amount of heat produced across the length of the conductor is directly proportional to the square of the current flowing through the conductor, right? And it is also found to be directly proportional to the resistance offered by the conductor. Greater the resistance offered by the conductor, more is the amount of heat produced across it, right? And third is, it is directly proportional to the time during which current is made to pass through the conductor. The more the time the current flows through the conductor, the more the conductor gets heated up, right? So these were some observations which James Joule made. So combining all the three, what we get is H is proportional to I square R T. Now we are aware that in order to eliminate this proportionality sign, we need to introduce some constant. Here the constant is 1 by J. This is J. J is a conversion factor known as Joule's mechanical equivalent of heat. We have studied it in +1 as well. So J is constant known as Joule's mechanical equivalent of heat. It is known as Joule's mechanical equivalent of heat. Right? Now here, we must be clear about the value of J. The value of capital J, that is Joule's conversion factor, is different in different system of units. In MKS, it is very important from completion point of view. The value of J is 4.18 Joule per calorie. This is the value of Joule's mechanical equivalent of heat in MKS system. In CGS, the value of J is 4.18. 1 Joule is 10 to 7 ergs, so 10 to 7 erg per calorie. This is the value of capital J in CGS. And in SI, this is very important because we prefer SI system only. The value of J is found to be 1, that is unity. So in SI, the value of J is 1. Therefore, in SI, H may be written as I square RT. So this is the expression for the amount of heat produced when current I is made to pass through a conductor offering resistance R for time T. So I square RT. This is the mathematical expression for Joule's heating effects of current. Clear, students? Now there are various other expressions as well. You can convert, or you can rather write H in terms of V, isn't it? Also, let's try. So we are aware from Ohm's law, we are aware V is equal to IR. V is the potential difference, I is the current, and R is the resistance offered by the conductor. So in place of I, we can write V by R. So what we get is H is equal to V by R whole square into RT. So we'll be left with V square by R into T. So this is another expression for the amount of heat produced. H is equal to V square by R multiplied by time. There is still another expression. This is the first one. This is suppose the second one. There is still another expression. What we can do is I square RT. In place of R, you can write it as V by I multiplied by T. So what we get is H is equal to VIT. So this is the third expression. So students, these are the various expressions for the amount of heat produced across the or throughout the length of the conductor when current is passed through the conductor for a finite time. So these are the various expressions, right? So one is H equals to I square RT, the second one is H equals to V square by RT, and the third one is H equals to VIT. Here, just consider on the expressions, and here I would like to mention one very, very important fact. Here it will appear that heat is directly proportional to resistance, and here it will appear that heat is inversely proportional to resistance. The same expression for the heat, but two different results, right? Here it will appear as if it is directly proportional to R, and here it is inversely proportional to R. But students, keep this in your mind, and it should be crystal clear to you that they are not contradicting each other. Actually, H would be directly proportional to R only when current is constant. And here, H would be inversely proportional to R only when potential difference is constant. So these are two very, very important key points. So I'll write it over here. If current is constant, then the amount of heat produced is always found to be directly proportional to the resistance. This is a very, very important concept. And second, if potential difference is constant, if V is constant, then amount of heat produced is inversely proportional to the resistance offered by the conductor. So they are not contradicting each other. They will satisfy these conditions under several conditions. So H is proportional to R only when current is constant, and H is inversely proportional to R only if the potential difference is constant. Clear, students? So preferably while tackling numerical problems involving heating effect and where the conductors are connected in series, ensure to make use of this particular formula. And in parallel combination where potential difference is constant, this is more preferable expression to be used in such cases. Right, students? So, once again I repeat, James Joule experimentally found that when current is made to pass through a conductor for a given time, then amount of heat is produced or the conductor get heated up. The amount of heat produced is directly proportional to the square of the current flowing through the conductor. It is found to be directly proportional to the resistance offered by the conductor, and it is directly proportional to the time for which the current flows through the conductor. So, mathematically we can write in SI H equals to I square RT, or H equals to V square by R into T, or H equals to VIT. So, these are the three different expressions for the amount of heat produced across a conductor when current is made to pass through it. Clear, students? And there are various applications of heating effects of current. Actually, it won't be wrong to say that almost all the electrical appliances that we use in our daily life are based on Joule's heating effects of current. Like electric iron, then electric heater, geyser, electric iron. These all are the daily usable electrical appliances which are based on heating effects of current. All these consist of coil through which when the current is made to pass, it gets heated up. So electrical energy gets converted into heat energy. Clear, students? So we'll have a mathematical verification of this as well, right? So there is a qualitative study as well, right? Why heat is produced? Why is it so? Now look, students, let me theoretically try to explain it. We are aware inside a conductor, the electrons act as charge carriers. The positive ions, they keep on vibrating about their mean position. They are immobile. Only the electrons drift about here and there randomly, right? And under the influence of some external source, the electrons tend to drift in a particular direction, that is from lower potential to higher potential. Now as we are aware, the electron density in conductors is very large. So during the drift of electrons, they very often collide against each other, and also while they drift from one end of the conductor to the other, they very often collide against the vibrating ions. And during each such collision, their motion gets hindered, and that is what resistance is all about. Now during each such collision, a part of kinetic energy of the electron gets transferred to the vibrating ion. So as a result, what happens is the average thermal energy of the conductor tends to increase, and as the thermal energy of the conductor increases, it results into the rise in the temperature of the conductor, or rather it produces heating effect. So that's the theoretical explanation. So this is how when the current is made to pass through a conductor, the conductor definitely will get heated up. The extent to which it will get heated up, it depends upon the resistance offered, it depends upon the amount of current passed through the conductor, it depends upon the time for which the current is made to pass through the conductor. Right? So all these factors are to be kept in mind. Now, let us derive this formula mathematically. We will try to derive all these expressions mathematically by using the concept of potential difference. Right? So students, we all are aware of the concept of potential difference, isn't it? It is actually the amount of work done per unit charge in making the charge to move from one point to another so as to complete the circuit. So suppose this is the source which is providing a potential difference of V. This is the higher potential, this is a lower potential. VA is considered to be greater than VB. Now as per definition, the potential difference between the 2 points, A is greater than B. So VA minus VB, which is considered to be V. It is the work done per unit charge in moving the charge from one terminal to the other terminal so as to complete the loop. Isn't it? This we are already aware of. So work done by this source of EMF in maintaining a constant current would be given by potential difference multiplied by charge. Now, as we are aware from Ohm's law, V is equal to IR. Q in terms of current would be I into T, because we are aware current is the rate of flow of charge and potential difference is I multiplied by the resistance offered by the conductor. So what you get is W is equal to I square RT, isn't it? So this is the work done by the source of EMF in maintaining a constant current through the conductor, and this is what is electrical energy is all about. And this electrical energy, students, get converted into heat energy, perfectly in accordance with the law of conservation of energy. Therefore, the amount of heat produced across the conductor is I square RT. This amount of work done appears across the conductor in the form of heat. And as I have stated earlier, there are three expressions. H equals to I square RT. In place of I, substitute as I equals to V by R. So what you get is H is equal to V square by R into T. And what will be the third expression? Third expression will be H is equal to VIT. So these are the three expressions for the amount of heat produced when current I is made to pass through a conductor. I hope you have understood the concept completely, isn't it? So now we have discussed electric energy. We are also over with Joule's heating effects of current. Now it's time to concentrate on this particular topic, electric power and its various expressions. In plus 1, in the previous class, we have discussed about mechanical power. In plus 2, we are going to discuss about electric power. Power is actually the rate of doing work. Nothing new in it, rate at which work is done. Here, the electric power of a circuit is defined as the rate at which electrical energy is consumed, isn't it? So, any device will have some electric power which will be defined as the rate of consumption of electrical energy by that device. That is known as power. So, power is actually the rate of consumption of electrical energy, which is electrical energy divided by time. Rate means divided by time. So the rate of consumption of electrical energy of an electric circuit is known as its power. Clear, students? So regarding its unit of power is, SI unit of power is watt. SI unit of electrical energy or any energy in SI, its unit is joule. And time obviously it's measured in second. So the electric power of a circuit or any electrical device is said to be 1 watt if it consumes 1 joule of electrical energy in 1 second. Clear, students? So this is how 1 watt is defined. There are some other units of power as well. 1 kilowatt, it is 1000 watt. 1 megawatt, it is 10 raised to the power 6 watt. And then 1 horsepower. This is also a unit which we denote to express power. It is 746 watt. 1 kilowatt, it is 10 raised to the power 3 watt. 1 megawatt, it is 10 raised to the power 6 watt. So these are the various units for measuring power. Now regarding dimensional formula, it's again very simple. Electrical energy has got the dimensions of kg. It is force into distance, isn't it? So kg meter square per second square, isn't it? And time, it is second. So the power in terms of the basic units or fundamental units would be like this. So the dimensional formula for the power would be mL2T minus 3. This is the dimensional formula for electric power. Right, friends? Now what to do is, let's try to find out the expression or various expressions for the electric power. We are already aware of the various expressions for the amount of heat produced, so we can make use of those expressions only. Now look, first is electrical energy. As we are aware, it appears across the conductor in the form of heat. So one of the expressions for the heat is, heat consumed or heat emitted is I square RT, isn't it? Divided by time. That is, power would be equal to I square R. This is the first expression. Second, electrical energy may also be written as V square by RT, just now we have discussed, divided by time. That is, power may also be written as V square by R. This is the second expression for the power, isn't it? And third is, electrical energy or the amount of heat produced may also be written as V into I into T, divided by time. That is, power may also be represented in terms of VI as V multiplied by I. So these are the three different expressions for the power. Clear, students? So here again, I must mention that very, very important point. Here power is directly proportional to R. Over here power is inversely proportional to R. So first time it might give us the impression as if both are contradicting each other. But students, it is not so. Because power is directly proportional to resistance only when current is constant. And power is inversely proportional to the resistance only when potential difference is constant. Isn't it? So therefore, when current is constant, it is only then power is directly proportional to resistance. Power of an electric circuit or power of an electric device will be directly proportional to the resistance offered by its coil only if the current is constant and if potential difference is constant across the electric circuit or across the two ends of an electric device, then power is inversely proportional to the resistance. So actually they are not contradicting each other. They are satisfying these relations only under special conditions. Isn't it? So there shouldn't be any sort of confusion. And as I stated earlier, in numericals concerning electric power of circuits involving series combination of devices, make use of this particular formula. P equals to I square R. And in case of parallel network of electrical components, try to make use of this particular formula. Because in parallel, the potential difference across each of the electrical devices is constant, while in series, the current is constant. Right, students? So, these are the various expressions for the electric power. So, electric power of a device is the rate of consumption of electrical energy by that particular device. So, if I say I have purchased an LED or I have got a LED bulb of say 10 watt, what does it mean? It simply means that the LED bulb is consuming 10 joule of electrical energy in 1 second. Clear, students? So now let's find out the relationship between kilowatt hour and joule. Joule, as we are aware, it's the SI unit of any form of energy, and kilowatt hour, it is also the unit of energy, but it is the unit of commercial unit of electrical energy. It is actually bought, board of trade unit. So let's discuss this particular topic. Commercial unit of electrical energy. So the electricity bills is always expressed in terms of kilowatt hour. Suppose a household consumes 30 units of electricity in a month. So 30 units means 30 kilowatt hour. Right? So the commercial unit of electrical energy is kilowatt hour. Kilowatt hour. It is also known as watt. It is actually board of trade unit. It is board of trade unit. So the commercial unit of electrical energy is kilowatt hour, and it is also known as watt, board of trade unit. Right? So let's find out the relationship between the commercial unit of electrical energy and the SI unit of electrical energy. We are aware SI unit of electrical energy is joule, while commercial unit of electrical energy is kilowatt hour. So let's find out the relationship between these two. Now we are aware power is equal to energy or work done per unit time, right? Therefore, energy would be equal to power multiplied by time. So, kilowatt hour. Kilowatt hour. Look, if this is expressed in kilowatt, this is expressed in hour, then it will become kilowatt hour, which will be the unit of energy, isn't it? So, kilowatt hour is indeed the unit of energy. So, kilowatt hour would be kilowatt. As I stated, it is equal to 10 raised to the power 3 watt. 1 hour. Let's try to convert this 1 hour into seconds. So 1 hour is equal to 60 minutes and each minute is equal to 60 seconds. So what do you get is 36 multiplied by 10 raised to the power 5 watt second. Watt second is joule, isn't it? So it can be written as 3.6 into 10 raised to the power 6 joule. So 1 kilowatt hour, it is equal to 3.6 into 10 raised to the power 6 joule. So this is the relationship between the commercial unit of electrical energy and the SI unit of electrical energy. So students, I hope you have understood the theoretical topics. We have discussed electric energy, we have discussed Joule's heating effects of current, its application, the theoretical explanation, the mathematical verification, and then obviously we have discussed electric power, its 3 various expressions, and last we have considered the commercial unit of electrical energy. So students, do revise this topic thoroughly and we'll continue in the next lecture then. Till then, do take very good care of yourself and bye-bye. Thank you.